So we talk about the photon and the matter wave. So so this is the outline. This is the outline. So okay, the photon, the quantum of light. So in 1905, Einstein proposed that the electromagnetic radiation, or simply light, is quantized and exists in elementary amount quanta. At that time, a call it quanta 就是光量子。That we now call photons， 这个就光子嘛，光子。According to that proposal, the quantum of the light wave of the frequency F has the energy E equals hf. I suppose you should have learned it before. E equals hf, which means that h is a constant called the Planck constant, which is 6.63 times 10 to minus 34 joule per second. So which is a very, very important constant in the quantum mechanics or in modern physics. Planck constant. So or similarly, we can write it using the reduced Planck constant, which is h over 2 pi, So in this case, we can express E to be h bar over omega, h bar times omega, which is nothing but E equals hf. So we divide h by 2 pi and then multiply f by 2 pi. So the first term is h bar, and then the second term is omega. So this is nothing special. So if you still remember, 1905 is a very important year for the modern physics. So Einstein not only proposed the photoelectric effect, and also proposed the special relativity. So here is a sample problem. So a sodium vapor lamp is placed at the center of a large sphere that absorbs all light reaching it. So the rate at which the lamp emits energy is 100 watt. Assume that the emission is entirely at the wavelength of 590 nanometer. So this is the wavelength of the light. At what rate are photons absorbed by the sphere? So at what rate, which is actually the rate emitted is the total power emitted over E. E is actually the single energy of the photon. So this is 100 watt, and then or maybe I just make some calculation here first. So so this is actually P emit, and then E is hf. And you know that C equals F lambda. So this is a very important equation. So actually we can, because we know the wavelength rather than the frequency, so we need to eliminate F. so that it becomes P emit and then HC over lambda. So we put lambda at the top. Okay. So we can substitute the number. So this is 100 for the P emit, and then lambda is 590 times 10 to minus 9. And then over Planck constant is 6.63 times 10 to minus 34. And then C is 2.998 times 10 to the 8th power. So the answers would be 2.97 times 10 to 20. Photons per second. Photons per second. Yeah, because this is the power, which means the energy per second. So this is the energy per photon. So after you divide it, so it will be the number of photon per second emit. Any questions? Okay, so we talk about the photoelectric effect. So here, an apparatus used to study the photoelectric effect. So the incident light shine, here. So from the right side, shines on the target, ejecting electrons which are collected by the collected cup C, collected cup C. Which means that as the light incident from the right side to here on this target, so the electron here will absorb the light. After absorb the light, then it will have more energy, and as long as it has more energy, it will be able to escape and then hit the cup. So it's just like originally this is open circuit, and then if you use some light to shine on this target, and then some electron will go to this way. It feels like there are some current going in this loop counterclockwise, right? So the incident light shine on the target, ejecting the electron which are collected by the collector cup, and then the electron move in the circuit in a direction opposite to the conventional current arrows. So the battery and the rebel resistor are used to produce and adjust the electric potential difference between T and C. So actually we can adjust the battery here. Yeah, actually you can imagine this is, maybe you can imagine this is the ground. You can imagine this is the ground, so that we have a V1, this is V2, this is V2. So that for this point, this is minus V2, and this point is V1. So if you have a sliding contact here, you can have a voltage, any voltage between minus V2 and V1. You can choose a voltage at this point. Okay, so we then vary V until it reach a certain value called the stopping potential. So as long as this voltage is the V stop, at which point reading the meter A has just dropped to zero. When V equals V stop, the most energetic ejected electron are turned back just before reaching the collector. And then Kmax of this most energetic electron is Kmax equals E times V stop. Because you can imagine, as long as you have T here, and then maybe I make this cup like this. So assume this one is ground, this one is ground, so this one is ground. So this one is ground, and then this one is V stop, maybe a negative voltage, which means that suppose you have a electron here going from the left to right, it has a potential to make this electron going back. So as long as this electron has large enough kinetic energy, it can reach this cup. Otherwise, it will be pushed back by the potential and going back. So and in this way, we cannot see any current. As long as this Kmax is larger than E times V stop, then some of the electron can reach this cup, and then there will be some current going in this loop. So we can just adjust this V stop to observe what is the Kmax. So here, this is the second photoelectric experiment. So you can see here, if the frequency f of the incident line is vary, for the first experiment, we only changing the voltage here, and we can observe something called the stopping potential, V stop here. And here we try to vary the frequency of the light. So maybe this segment is the visible light. For the left side is infrared. For the right side is ultraviolet. And actually, for the right side, it has higher frequency, which means it has high energy because you have E equals HF. So the higher frequency, the light is it has more energy. So if the frequency of the incident line is vary and associate stopping potential is measured, then report V stop versus F as shown in the figure is obtained. So the photoelectric effect does not occur if the frequency is below a certain cutoff frequency. So we can actually measure some point, maybe this point. So we can measure 5 points with different incident light. So these two are in ultraviolet. This one may be still ultraviolet, and this is the edge, maybe a purple light, and this is the blue light. So we have 5 experiments. So they are roughly line on a line. So we can just connect together with a line or fit it with a line, and we find that as long as there is a frequency called the cutoff frequency F0. So if the incident light is has a frequency lower than F0, no matter how intense you make the light, there are no photoelectric photoelectron 就没有那个光量子啊的出现，就是说我们可以改变那个光的那个频率啊，然后我们找到那个不同的 V stop， 找到不同的截止电压啊。那当频率低过这个 F0 的时候啊，无论你那个光多强啊，它都没有那个光子可以逃离啊，可以逃离。Okay, so if the wavelength is greater than the corresponding cutoff wavelength, this is so no matter how intense the incident light is， 就是无论那个光多强的话，它都不会，就是只要频率太低，或者说换句话说是那个波长太长的话，长过那个 lambda zero 的话 ，so the electron within the target are held there by electric force. To just escape from the target, an electron must pick up a certain minimum energy phi, where phi is a property of the target material called work function 公函数。那个公函数是跟材料有关的，不同的金属的公函数不一样啊。So if the energy HF transferred to an electron by photon exists the work function of the material, which means HF is larger than the phi, the electron can escape the target. 所以我们可以写成就是这个phi 等于 hf0 phi 等于 hf0。So we can so Einstein sum up the result of such photoelectric experiment in the equation like this, which is a very simple linear equation. So phi is the work function, and then K is the maximum kinetic energy of the photoelectron, and then this is the energy of the incident photon. So we have HF equals K max plus phi. So actually we can just move this one to the left side. So we have K max equals HF minus phi. And then we can divide both sides by E. So we have the right side like this, and then actually the left side is like this, because on this page we have a K max equals E times V stop. So actually in high school you learned that y equals mx plus b. So here y is this v stop. So this is y equals x is f. So x. So h over e is the m. is the M. And then this intersect point here. This is B, mx plus B. So which is a negative number because cut here. So if you, but actually it does not, we does not have this part because there are no photoelectric effect for that part. It is actually a non-linear one rather than linear. It is linear as long as f is larger than f0. So actually B is phi over minus phi over E, and the slope of this line, is actually h over E. So it does not depend on the material for the slope because h is a constant, which is a Planck constant. E is also a constant, which is a 1.6 times 10 to minus 19 Coulomb. So actually the slope is a constant, but the intersect point depends on the material because phi is the work function. Phi is the work function which depends on the material. So for different material, this line may be going up or down. Okay, so here is a sample problem. So find the work function phi of the sodium from the figure. So this is the sodium, the curve for the sodium. So so when f equals f0, v equals v stop, and phi equals hf0, because I just now mentioned that actually phi is nothing but hf0. So in this case, it is 6.63 times 10 to minus 34 times this f0 is roughly 5.5 times 10 to the 14 hertz. If you read on the figure, so this is 5.5 times 10 to 14. So it will be 3.6 times 10 to minus 19 joule, or you can convert it to EV, which is 2.3 EV. So this is the work function. This is the work function of the sodium if you according to the photoelectric experiment. So actually we only need this point to calculate the work function. Okay, so the next we talk about the photon have momentum. Photon have momentum. Because when we talk about duality, which means that there are some variables. For particle. For particles. Also, there are some variables for waves. So for waves, we have a wave number, and also omega. Or in 3 dimension, we have a k can be a 3 vector. And for particle, we have momentum. In 3 dimension, which is a vector. Also, we have energy. So this is variable for particle, and for variables for waves. But actually, there are different equations which can explain some phenomenon about the light or the photons. Of course, when we learn the chapter 33, we learn the EM wave, so we know that for the wave is like cosine omega kx minus omega t. Somehow like E equals EM cosine kx minus omega t. So we have a k here, we have omega here. So which tells you all what is the direction and also the frequency of the wave, of the EM wave. And here we also talk about the energy of a particle, the photon. We have E equals HF or H bar omega. And here we also talk about the momentum of the photon. According to this called Compton effect. So in 1916, so after Einstein have finished the general relativity, he goes back to observe this stuff. So Einstein extend his concept on light quanta, or we call it photons now, by proposing that a quantum of light has linear momentum. So for a photon with energy HF, the magnitude of that momentum is like this. Like this. So as long as we have this equation, it can explain this experiment. And later on, someone called de Broglie used the same equation for the matter wave. So for this one, E is the variable for particle, and F or omega is the variable for wave. So they link it together, and then for this equation, we have on this textbook it is written like P equals HF, which is the E over C. And then HF is actually F is C over lambda. So finally it is written as P equals h over lambda, or we can write it as a h over 2 pi and then 2 pi over lambda. So this is this one. So this is h bar times k. So some of the textbook using this will be better looking. And you may ask why. Why E equals PC? You may ask why. If you still remember, at the beginning of the first hour, we learned that E square equals PC square plus MC square quantity square. So now photon doesn't have West mass, so this reduced to 0 for photon, and in that case E equals PC. Use something like that. So we have a E equals PC for a photon. And of course, this one has P on the left side and K on the right side. And P is the variable for particle, and K is the variable for wave. So actually, these two equations link the variable between the particle and waves. Okay, so this is the on the right side. This is the Compton's apparatus， 就是那个仪器。So a beam of X-ray of wavelength lambda equals 71.1 picometer is directed onto a carbon target T. Carbon 就是一块碳，然后这里有个 incident X-ray X-ray 从这边打过来。The X-ray scatter from the target are observed at various angle phi to the direction of the incident beam. The detector measures both the intensity of the scattered X-ray and their wavelength. 所以这个实验做过什么事情呢？就是中间呢，它有一块碳的晶体它可能有一些原子排列的，可能有一个晶体的结构，可能排列的蛮好的。那从左边啊，它有一些X-ray 打过来，那 X-ray 它是一个高能的射线嘛，那所以它的频率很高，波长很低，所以它穿透能力很高，所以它有可能啊，它就是刚好正中红心它就反弹回来。它也有可能啊，就是打到一个之后，它就折射，它有可能折射不同的角度，那然后它就用一个仪器啊，从不同的角度去看，折射的那些光的波长有什么的改变 ，lambda pi， 那他就发现说，这个 lambda prime 跟这个 phi 是有关系。你折射的角度不一样，它的波长的改变也就不一样。那这个啊，需要用到动量这个概念来描述，才能够，因为正常如果它只有波的特性的话，它频率是不会改变的。但是实际上它的 lambda 会随着它折射的角度而变化。So this graph shows for measurement for measurement. So if phi is 0, which means that the light is directly go through, and you can observe that. So this is the original wavelength. This original wavelength of the incidence X-ray. And if it is 45 degree for the phi, which means that this is 45 degree. This makes you can see there are two peaks here. There are two peaks here. Although these two peaks are not separate a lot, but actually, but at least you can observe there are two peaks there, slightly separate. And then for this case, if phi is 90 degree, which means that the light going this way, then you can see the delta lambda is even larger. You can see that one peak is here, another peak is there. So you can see this one is the original wavelength. This is original wavelength. This is original wavelength. And then this one becomes the new wavelength. Okay, so if it is 135 degree, which is like that, so this is 90 degree, this is 45 degree, this is 0 degree, this is 135 degree. So if it's 35 degree, delta lambda is even larger. So this is something like maybe the delta lambda is 1 or 2 picoM. For this one, it is maybe 2 or 3, maybe 3. This one is more or less close to 5 picometer. 5 picometer. So which means that the delta lambda is related to the scatter angle phi. Note that the Compton shift, delta lambda increase as the scatter angle increases. Okay, so maybe we just stop here.